Imagine you're reading a conversation in a database, and you see the answer before you see the question. That's deeply wrong, it violates causality. If someone answered a question, they must have seen the question first. The answer causally depends on the question. The question must come before the answer. This intuition is the foundation of causal consistency. Causality imposes ordering, cause must come before effect. A message is sent before it is received. A row must be created before it can be updated. If Alice told Bob the football score, Alice must have seen the score before Bob heard it from her. The book defines it this way: operations A and B are causally related if A happened before B, meaning B might have known about A, or depended on A. If neither A nor B happened before the other, they are concurrent, there's no causal link between them. Here's the subtle but critical point: causality defines a partial order, not a total order. In a partial order, some pairs of operations are comparable, causally related, and some are incomparable, concurrent. You can always say which one of two natural numbers is greater. But you cannot always say which of two concurrent operations happen first, they happen in parallel, and there's no fact of the matter. Linearizability, by contrast, defines a total order as if there's a single timeline on which every operation appears at one instant. This is stronger than causality requires. And that excess strength is exactly what makes linearizability expensive. The key insight from this chapter: causal consistency is the strongest consistency model you can achieve without sacrificing availability under network partitions. If your system only needs causal ordering, not full linearizability, you can have performance and availability that resembles eventual consistency, while still maintaining meaningful correctness guarantees. So we want to capture causal order without the overhead of linearizability. The naive approaches don't work. You can't use physical clocks. Clock skew means a causally later event might get a smaller timestamp than the event it depends on. You can't have each node generate odd or even numbers, the counters diverge and can no longer be compared across nodes. You can't pre-allocate blocks of numbers, then operation 1500 on node A might actually be causally before operation 50 on node B. In 1978, Leslie Lamport published a solution that is elegantly simple. It's called the Lamport timestamp, and it remains one of the most cited papers in all of computer science. The idea: every node and every client keeps track of the maximum counter value it has ever seen. The timestamp for any operation is the pair, counter, node ID. When a node processes an operation, it increments its counter by 1. But here's the key: if the node receives a message that has a higher counter than its own, it immediately jumps its counter up to that maximum, then increments. Why does this work? Consider the causal chain. If operation A causally precedes operation B, then by the time B executes, the node executing B has already seen A's timestamp. So B's counter will be at least as large as A's counter, and after incrementing, strictly larger. Therefore, a causally later operation always has a larger Lamport timestamp. The timestamps are consistent with causality. For disambiguation, when two events have the same counter, the node ID is used as a tiebreaker. Every timestamp is unique. This is different from version vectors, which we saw in Chapter 5. Version vectors can tell you whether two operations are concurrent. Lamport timestamps cannot, but they're more compact. The trade-off is deliberate. Lamport timestamps give total order consistent with causality, version vectors distinguish concurrency. However, and this is important, Lamport timestamps alone are not sufficient. They tell you the order after the fact. They can't tell a node, in real time, whether it's safe to declare an operation successful. For that, you need total order broadcast. Here's the problem that Lamport timestamps expose but cannot solve. Two users simultaneously try to register the same username on two different nodes. After the fact, you can compare their Lamport timestamps and say which one had the lower timestamp, that one wins. But right now, at the moment node A receives the registration request, it doesn't know whether node B is concurrently processing the same request. It can't declare victory without checking all other nodes, and if any node is unreachable, the whole system grinds to a halt. The problem is that the total order of operations only emerges after you've seen all the operations. If you don't know what other operations are coming, you can't know where in the total order your operation will land. What you actually need is for the order to be fixed at the time messages are delivered, not reconstructed after the fact. This is precisely what total order broadcast provides. Total order broadcast is a protocol for exchanging messages between nodes with two properties. First, reliable delivery: no messages are lost. If a message is delivered to one node, it is delivered to all nodes. Second, totally ordered delivery: messages are delivered to every node in exactly the same order. Think of it as an append-only log. Every node sees the same sequence of messages. Delivering a message is like appending to the log. Since all nodes process the log in the same order, they all reach the same state. This is the principle of state machine replication. Apache Zookeeper and ET to implement total order broadcast. In Zookeeper, every append to the log gets a monotonically increasing sequence number called a ZXID. This can serve as a fencing token for distributed locks. Here's the profound connection the book reveals: total order broadcast is equivalent to consensus. Solving one solves the other. And linearizable compare-and-set operations on a register are also equivalent to both. These three things, linearizability, total order broadcast, and consensus, turn out to be the same fundamental problem. Which is exactly why, to solve them, you need dedicated consensus algorithms like Raft, Paxos, and ZAB.